Let's talk about the magnetic force on a current carrying wire. So we just talked about the magnetic force on a charge that was moving perpendicular to some sort of magnetic field. That magnetic field could be created by like a bar magnet or a coil. Something else is creating that magnetic field though. Due to the cross product in our equation, we know V and B must be perpendicular. Or at least have some components that are perpendicular, and it's only the components that are perpendicular that will result in a magnetic force. Well, since current, we've defined current as the rate at which charge flows, and we've defined it as if positive charges were moving. Now, we do know fundamentally, microscopically, electrons are the one moving, but mathematically, if we just pretend it's positive charges moving, we'll get the correct answer. Because positive charges moving one way and electrons moving the opposite way give us the same overall direction. So we think about this magnetic force, Q times V, in very general terms, we can think of a wire. So let's say I have a wire carrying current. Well, this is a whole bunch of little pieces of charge, dq, traveling with some velocity. Well, velocity is a derivative of position with respect to time. Crossed with magnetic field. The definition of current is dq dt. ds, since every single piece of charge, if even all these little, we're pretending protons are moving, all of them would be moving in the same direction. So we can just call this the length of the wire to account for all of them. So our equation for the magnetic force on a current carrying wire looks like this. Now we do draw the vector above the L, but the direction is determined by the direction of I. So the direction of L is the direction of current flow. Direction of the current. So in this particular example above, we would say L points to the right. The magnitude of L is the length of the wire in the magnetic field that's created by a bar magnet or by a coil, whatever's creating the field in this region of space. Okay, so I would like, oops, come on. Sorry, I'm trying to get this picture to move up. No? Okay, it's not behaving. So I'll rewrite the equation right here. What do you think the answer to this is? correct answer is going to be B. This is figured out very similar to our force on the moving charge, because we can use the same right-hand rule for any cross-product equation. Whichever vector is first in the cross product, we will use our thumb to represent it. Now, of course, we don't know the direction of the current here. So we don't know what direction to put our thumb in yet. Our pointer finger or index finger will always point in the direction of the second vector in the actual cross product. In this particular case, we know that points into the screen. And we know that because of these X's that have been drawn. There's something creating a magnetic field in this region. So those X's represent into the screen. The result is always our middle finger. Well, if I have my index or pointer finger pointing into the screen, I do know the magnetic force must be upwards to levitate this wire, because it needs to counteract the force of gravity. So I point my index finger into the screen and rotate my wrists, or however I need to do it, to get my middle finger pointing up towards the top of the screen. So into the screen, rotate my wrist to get my middle finger pointing towards the top of the screen. That leaves me with my thumb pointing to the right. That means the current in here, I, must point to the right to get the force to point upwards. So that's why the current needs to flow left to right. If we wanted to find a numerical answer, which we don't have enough information to solve it completely, but we would say that the magnetic force was equal to the gravitational force. The magnetic force would depend upon the current, how much current is flowing through this wire, the length of the wire, but only the length within this region right here where the magnetic field exists. Any wire extending out, if there's no field out here, then we don't care about the length out there. It's only the portion of the wire that's actually in the region where the magnetic field exists. ILB, so equation up here, the magnitude would be ILB sine of phi. Phi is the angle between L and B, the two vectors we're crossing. And again, L is the direction of the current. That's how we determine L. Well, the current flowing left to right is making an angle of 90 degrees in this case with the magnetic field that points into the screen. Sine of 90 is 1. So ILB has to equal the force of gravity, mg. So depending upon what information potentially was given in a problem like this, we could solve for anything else. For example, if we knew the current and the length of the wire in that region, we could find the strength of the magnetic field needed to levitate the wire. Or we could find the mass of the wire if we knew the current and the field and the length. So there's a number of things that we could find. In the next video, we'll talk about the magnetic force that one wire exerts on another.